Welcome to this deep dive into the scientific principles behind self-experimentation and using your life as a laboratory for personal development. Today we're going to explore how you can accelerate your growth through rigorous self-experimentation and, critically, what psychological safeguards you need to avoid falling into the traps of bias and self-deception. Let's start with the fundamental scientific framework. In medical research, there's a concept called the N of 1 trial. This is a clinical trial where a single patient is the entire study. You become both the researcher and the subject. Traditional scientific studies involve hundreds or thousands of participants and tell you about average effects across a population. But an N of 1 trial focuses exclusively on you. The question is, what works specifically for your unique biology, psychology, and circumstances? Here's why self-experimentation is so powerful for personal development. Learning and skill acquisition follow what's called a power law. Let me show you the mathematics. The time t to perform a task decreases with practice according to this power law. T equals a times n to the negative b, where n is the number of practice trials, a is initial performance time, and b is the learning rate, typically between 0.3 and 0.5. What does this mean practically? It means that your first few experiments and iterations produce the most dramatic improvements. Early experimentation has disproportionate returns. Let's do a back-of-the-envelope calculation. If b equals 0.4, then your performance at trial 100 is about 1/4 of your performance at trial 10. You get 4 times faster through iteration and experimentation. The first core principle is rapid iteration cycles. Traditional psychology research might take months or years to design, execute, and analyze a study. But you can run personal experiments in days or weeks. Here's the experimentation cycle. You form a hypothesis, test it for 1 to 4 weeks, measure the outcomes objectively, analyze the data, and then iterate. The faster you cycle, the faster you learn about yours. Let me give you a concrete example. Suppose you want to optimize your sleep for cognitive performance. Here's how you'd structure this as a rigorous self-experiment. Your hypothesis might be, sleeping exactly 7.5 hours per night will optimize my morning cognitive focus better than my current 6 to 8 hour variable schedule. You'd use an ABAB design. 2 weeks of baseline with your current sleep pattern, 2 weeks of the fixed 7.5 hour intervention, return to baseline, then retest the intervention. This controls for practice effects and seasonal variations. What would you measure objectively? This is critical. You can't just rely on how you feel because of bias. You'd measure reaction time using a standardized online test each morning, working memory span with the digit span test, mood using a validated scale like PANAS, actual sleep duration from a tracker, and control variables like caffeine intake. Now let's talk about the first major psychological safeguard you need: protection against confirmation bias. This is the tendency to search for, interpret, and recall information that confirms your pre-existing beliefs. Mathematically, confirmation bias means the probability of noticing evidence, given that it confirms your hypothesis, is much greater than the probability of noticing evidence that contradicts it. How does confirmation bias manifest in self-experimentation? Let's say you started taking a new supplement and you believe it will boost your energy. The biased thinker notices the days they feel energetic and attributes it to the supplement, while ignoring or explaining away the tired days. The scientific thinker tracks every single day and compares the distribution to a proper baseline period. The defense strategy is called pre-registration. Before you start your experiment, you write down exactly what you'll measure, how you'll measure it, and what results would convince you that your hypothesis is wrong. You must write down, what specific outcome would disprove my hypothesis? If you can't answer this, you're not doing science, you're just confirming what you already believe. The second major safeguard is protecting against placebo effects. The placebo effect is real and powerful. Studies show that 30 to 40% of people respond to placebo treatments. The observed effect in your experiment equals the true effect of the intervention, plus the placebo effect, plus random noise. You need to separate these components. Can you eliminate placebo effects in self-experiments? Not entirely, because you usually know what intervention you're doing, but you can minimize it. 4 strategies to minimize placebo. First, use objective measures like reaction time or heart rate variability, not just how you feel. Second, blind yourself when possible. For example, have someone else prepare supplements in identical capsules. Third, use active controls. Compare your intervention to another plausible intervention. Fourth, test multiple times with the ABAB design. Let me introduce you to a subtle but critical problem: regression to the mean. This trips up even experienced researchers. What is regression to the mean? It's the phenomenon where extreme measurements tend to be followed by measurements closer to the average. This is pure statistics, not a real effect. If x sub 1 is your first measurement and x sub 2 is your second, then x sub 2 equals r times x sub 1 plus 1 minus r times the population mean mu plus random error epsilon, where r is the test-retest correlation, typically 0.5 to 0.8. Here's the trap. Let's say you're feeling really unproductive and stressed, so you decide to start a new productivity system. Most likely, you'll feel better in a few weeks. But was it the system or just regression to the mean? You are at 2 out of 10 productivity, an extreme low point. 4 weeks later, you're at 6 out of 10. You attribute this to your new system, but statistically, you are likely to improve anyway just by regression to the mean. The defense is to always collect baseline data for at least 2 weeks before starting any intervention. This gives you a realistic estimate of your natural variation and average level. The third safeguard protects against the Hawthorne effect. This is the phenomenon where people change their behavior simply because they know they're being observed or measured. The classic study was done at the Hawthorne factory in the 1920s. Researchers found that workers increased productivity whenever they were being studied, regardless of whether the lighting was increased or decreased. The act of measurement itself changed behavior. Measured behavior does not equal natural behavior. The moment you start tracking something intensely, you unconsciously change it. Here's a practical example. When you start logging every calorie you eat, you naturally start eating less, even if you're trying not to change anything. This is the Hawthorne effect in action. The mitigation strategy is to use passive tracking whenever possible. Use automated tools that don't require conscious input. Phone screen time trackers, sleep monitors, activity trackers. These measure behavior without making you hyper-aware. Now let's address a critical issue that many self-experimenters ignore: statistical power. Can you actually detect a real effect with your sample size of one person? Effect size equals the difference between the two means divided by the standard deviation. This is Cohen's d. A small effect is 0.2, medium is 0.5, large is 0.8. Let's do a back-of-the-envelope calculation. How many days of data do you need to detect a medium-sized effect with 80% power at the standard 0.05 significance level? Using the approximation n equals 16 divided by d squared, for a medium effect size of 0.5, you need approximately 64 days of data. That's 32 days per condition in an A-B design. This reveals an uncomfortable truth. Most short self-experiments of 1 or 2 weeks per condition are severely underpowered to detect anything but very large effects. You need longer timelines or larger effect sizes to get reliable results. The second core principle is to measure what matters proximally, not just ultimate outcomes. Ultimate outcomes like happiness, success, or health are important, but too delayed and noisy to use as daily feedback. Instead of the vague distal goal of being happier, focus on the proximal behavior like meditating 20 minutes daily, and the lead metric like morning cortisol levels or heart rate variability that should change within days or weeks. The fourth safeguard protects against the narrative fallacy. This is our tendency to create coherent stories that explain outcomes, even when those outcomes are primarily due to chance. Humans are pattern-seeking machines. We find patterns even in completely random data. This was evolutionarily useful, but leads to false conclusions in self-experimentation. Consider this. The probability of a random streak of n coin flips all coming up heads is 0.5 to the n. For 5 heads in a row, that's only 3.125%. But with enough trials, streaks happen by pure chance. Here's how this manifests. You start a new morning routine on Monday. By Friday, you've had a great productive week. You create the narrative. The new routine caused the great week. But maybe it was just a good week that would have happened anyway. Your story is simple. New routine causes great week. Reality is complex. It was a random good week, plus the new routine, plus you happened to sleep well, plus work was less stressful, plus multiple other factors. The narrative fallacy makes us collapse this complexity into a single cause. The defense is to require replication. One good week proves nothing. Can you replicate the effect? Does it work the second time, the third time? Real effects replicate consistently. The third core principle is controlling for confounding variables. A confounding variable is something that affects both your intervention and your outcome, creating a spurious correlation. The confound affects both the intervention and the outcome, making it appear that the intervention caused the outcome when really the confound caused both. Here's an example. You notice that on days when you exercise in the morning, you have better mood throughout the day. You conclude that exercise improves mood. But wait, what's confounded here? Sleep quality is a confound. When you sleep well, you're more likely to have energy to exercise in the morning, and you're also more likely to have better mood. So good sleep causes both exercise and good mood, creating a spurious correlation. The control strategy is to measure potential confounds and statistically adjust for them, or to hold them constant. In this example, you track sleep quality and only compare days with similar sleep. An advanced technique is randomization. This is harder in self-experiments, but powerful when possible. You randomly assign which days you do the intervention. Flip a coin each morning. Heads you do the intervention, tails you don't. This breaks the connection with confounding variables because they're not correlated with a random coin flip. Example. You want to test if drinking coffee at 2 p.m. improves your afternoon productivity. For 30 days, you flip a coin at 2 p.m. Heads you drink coffee, tails you drink decaf that looks and tastes identical. Track your productivity from 3 to 5 p.m. The fifth safeguard protects against the sunk cost fallacy. This is continuing an experiment or intervention because you've already invested time and effort, even when the evidence shows it's not working. Rational decision-making should only depend on future costs and benefits, not past investments. But humans irrationally factor in sunk costs. Here's the scenario. You've spent 6 weeks carefully testing a new productivity system. Your rigorous data shows no improvement over baseline. But you feel like you've invested so much time, you should keep trying. This is the sunk cost fallacy. Irrational thinking says, I've spent 6 weeks on this. I can't quit now. Rational thinking says, the data clearly shows no effect. The past 6 weeks are a sunk cost. I should move on to test something else. The defense is to pre-commit to a decision rule before you start. Write down, if I don't see at least X improvement after Y weeks, I will stop this experiment. Make the decision criteria objective and binding. The fourth core principle is using multiple converging measures. Don't rely on a single metric, because any single measure can be flawed, gamed, or influenced by confounds. Triangulation increases confidence. If 3 different types of measures all point to the same conclusion, you can be much more confident that the effect is real. Use subjective measures like mood ratings and how you feel, objective measures like reaction time tests and biomarkers, and behavioral measures like actual work output and time allocation. When all 3 converge on the same answer, you've found something real. Example for testing meditation. Subjective, daily stress rating on a 1 to 10 scale. Objective, morning cortisol level and heart rate variability. Behavioral, number of times you lose focus during work sessions. If all 3 improve, the effect is robust. Let me address a deep problem with self-experimentation. Generalization. What works for you in your current context may not work for you in different contexts, or may not work for other people. The effect of any intervention is a function of the person, the context, and the time. Change any of these variables, and the effect may change or disappear. What worked for you at age the 25th of may not work at age 35. What works during low-stress periods may not work during high-stress periods. What works when you're healthy may not work when you're sick. But here's the key insight. This is actually a feature, not a bug. The whole point of self-experimentation is to find what works for you specifically, in your specific context, right now. You're not trying to find universal laws. The practical implication is to periodically retest your findings. Every 6 to 12 months, rerun key experiments to see if they still hold. Your biology, psychology, and context change over time. Let me share the meta-principle that should guide all self-experimentation. Epistemic humility. This means maintaining appropriate uncertainty about your conclusions. Never be 100% certain about your self-experiment results, no matter how compelling the data seems. There are always potential confounds you didn't measure, biases you didn't eliminate, and alternative explanations you didn't consider. The probability that your conclusion is true should always be less than 1. Assign confidence levels. I'm 70% confident that this intervention helps. I'm 90% confident in this other finding. Never claim certainty. Let's do a final back-of-the-envelope calculation. What's the expected value of running rigorous self-experiments? Expected value equals the probability you find something useful times the value if you do find something, minus the cost of running the experiment. Let's be conservative. Assume you have a 20% chance of finding a genuinely useful insight, and if you do, it saves you 10 hours per week for the next 10 years. The experiment costs 40 hours to design and run properly. Expected value equals 0.2 times 10 hours times 52 weeks times 10 years minus 40 hours. That's 0.2 times 5,200, which is 1040 minus 40, equals 1,000 hours of net benefit, a 25-to-1 return on investment. Even with very conservative assumptions, rigorous self-experimentation has enormous positive expected value. The key is the compound benefits over time. Small improvements, rigorously validated, compound year after year. Let me summarize a practical framework you can use today to start rigorous self-experimentation. Step 1. Choose one specific, measurable variable to optimize. Not vague goals like be healthier, but specific metrics like reduce average morning resting heart rate by 5 beats per minute. Step 2. Pre-register your hypothesis and what evidence would convince you that you're wrong. Write this down before you start. Step 3. Collect at least 2 weeks of baseline data with no intervention. Measure everything you plan to track during the experiment. Step 4. Run your intervention for 2 to 4 weeks with daily objective measurements. Use automated tracking when possible. Step 5. Return to baseline for 1 to 2 weeks. If the effect is real, your metrics should return toward baseline levels. Step 6. Repeat the intervention. Real effects should replicate. If it doesn't replicate, you probably found a false positive. Step 7. Analyze your data using multiple converging measures. Don't cherry-pick the one metric that looks good. Look at the whole pattern. Step 8. Assign an honest confidence level to your conclusion. How certain are you really? 60%? 80%? Be intellectually honest. Let me leave you with final thoughts. Science is fundamentally a method, not just a collection of results. The scientific method is about systematic doubt, rigorous testing, and honest acknowledgement of uncertainty. Self-experimentation is powerful precisely because it's personalized. Large population studies tell you what works on average, but you're not average. You're a specific individual with specific genetics, habits, context, and goals. But with that personalization comes even greater need for rigor, not less. You're more vulnerable to bias when testing on yourself because you're emotionally invested in the outcome. Remember, the greatest scientists in history are those who most actively tried to prove themselves wrong. Richard Feynman said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." When you run self-experiments, be your own harshest critic. Actively look for evidence that contradicts your hypothesis. Question every positive result. Demand replication. This is how you build genuine self-knowledge rather than comfortable self-delusion. The reward for this discipline is profound. A life systematically optimized for your specific biology, psychology, and goals. Not based on general advice or population averages, but based on rigorous evidence about what actually works for you.